Jai Hind everyone. This is Jyoti Sharma, Assistant Professor in the Department of Electrical and Electronics Engineering, Ajay Kumar Garg Engineering College, Ghaziabad. Today we are going to cover the topic phasor diagrams of transformer, which is under the subject Fundamentals of Electrical Engineering, which is having a code of BEE 101 under AKTU. Okay, so under the unit 3 of this subject, which is transformers, we are having various phasor diagrams depending upon the working of transformer. Likewise, we used to have, in total we are having 5 phasor diagrams. The very first one is regarding the idle transformer, which is working on no load condition, then a practical transformer which is working on no load condition, and then the practical transformer when working on loaded condition. Now for the loaded condition, we can be having a resistive load, we can be having an inductive load, or we can be having an capacitive load. Depending upon that, we will be having 5 phasor diagrams. So moving on with the first phasor diagram, that is the phasor diagram of an ideal transformer on no load, right? So if at all we want to know the phasor diagram of an ideal transformer on no load, for that first we require what will be the characteristics of an ideal transformer, right? So if at all I go with an ideal transformer, what will be its characteristics? So if at all I see, its very first characteristic should be, it should be having 100% efficiency, and if it is to be having 100% efficiency, that means it should have 0 losses, right? It should have 0 losses, no iron loss, no copper loss. Fine. If that is so, the efficiency would be 100%. Then another property what we want is, if this has to happen, that the efficiency should be 100%, then if the efficiency has to be 100% and later on there shouldn't be any voltage drop. If there hasn't any voltage drop, then what is it meant? It meant that the winding resistance is 0. So the second property should be that the winding resistance is 0, so that there is no voltage drop, right? Then third one, there should not be any leakage flux. That means the 100% of the flux which is produced in the primary coil, that 100% of the flux is linking with the secondary winding, right? So there is no leakage flux, so there is no leakage reactance, so there is no voltage drop in the leakage reactance as well, right? So there is no leakage flux. Fourth, last one, that the permeability of the core should be very much high, right? If the permeability of the core is very much high, then obviously the core requires a very small amount of current to get it magnetized, right? If the core has to magnetize completely, so it will be requiring a very small current to get it magnetized, right? So these very small amount of, very negligible amount of current would be required for magnetizing the core of the transformer. So these are the 4 qualities or 4 characteristics for an ideal transformer. Keeping all these 4 characteristics in mind, if we just go with the phasor diagram of the ideal transformer on no load, what is going to happen? Okay, let's see. First we want to have a reference phasor, and for the reference phasor we will be having that quantity as a reference which is common to primary and secondary circuit both, and that is the flux. So we will keep the flux as our reference phasor. Fine. Now our second quantity, induced EMF, right? The primary induced EMF. As the flux is alternating, we will be getting an primary induced EMF in the primary winding, which is what we call it as E1, and this induced EMF will lag the flux by 90 degree, right? That we must have seen in the derivation of the EMF equation of a transformer, that this induced EMF will lag the flux by 90 degree. So the E1 would be represented lagging the flux by 90 degree. Later on, V1 is the supply voltage. V1 would be, if we see what is the relationship between V1 and E1, then V1 is equals to minus of E1 in phasor, right? This is the induced EMF. This will oppose the very cause producing it. What is the very cause producing it? The sinusoidal supply, right? According to Lenz's law, it will be opposing it. So V1 must be equals to minus of E1. E1 is already plotted. So where should be V1 in antiphase to it? So V1 would be here. Once again, what is the input current to the transformer at no load condition? At no load condition, the current taken by the ideal transformer, that is only IN, the magnetizing current. The magnetizing current, this is the current which is required to magnetize the core. As there is no losses, so the transformer doesn't require any current to make over with the losses, right? It is not going to make over with the voltage drop, it is not going to make over with the losses. This is the only current taken by an ideal transformer to get the core magnetized. And as the permeability of the core is very high, this magnetizing current is having a magnitude, a very small magnitude, right? This is nearly, this magnetizing current, if at all I compare, this is nearly 2 to 5% of the full load current. In fact, 2 to 3% of the full load current. So this magnetizing current is very small. Say if at all I say 100 is the rated current of the full load current of the transformer, primary current of the transformer, then the magnetizing current would be 0.2 to 0.5, right? So the magnitude of this current is very much small. Why it will be in the phase with flux, as I have shown you. This is in phase with the flux because this is the current which is responsible for the production of the flux, right? So this magnetizing current would be in same phase with the flux. Now moving on. So we have plotted the flux, we have plotted the magnetizing current, we have plotted E1. Now the secondary parameters. Now in the secondary, as the secondary, it is no loaded, right? There is no load in the secondary. So there will not be any I2, there will not be any secondary current flowing, but we will be having an induced EMF and the secondary terminal voltage, right? So the secondary induced EMF, that is once again an induced EMF, will be lagging the flux by 90 degree. But its magnitudes definitely depends upon whether the transformer is a step up transformer or a step down transformer. Considering or just assuming that the transformer what we are working is just a step up transformer. So if that is the case, obviously we will be having E2 greater than E1, but it will be in the same phase as that of E1, right? If it is a step down transformer, obviously this E2 would be smaller in magnitude compared to E1. And what about V2? V2, it is no supply voltage, it is just the terminal voltage which will be equal to the secondary induced EMF. As there is no voltage drop in between, there is no winding resistance, there is no leakage reactance. So we are having E2 is equals to V2. So this is the phasor diagram for an ideal transformer on no load condition. Moving on with the second one, this was the very first phasor diagram. Moving on with the second phasor diagram, that is the phasor diagram of an practical transformer under no load. So if it is a practical transformer on no load condition, what is the change going on in this, right? So once again we are keeping flux as our reference, some things are going to remain same. Then once again the induced EMF. The induced EMF, primary induced EMF E1 is going to be lagging the flux by 90 degree. Done. Then the primary supply voltage, that is V1, is going to be in antiphase, as once again V1 is equals to minus of E1. Still, again, we are still not introducing the winding resistance right now, right? We will be introducing it in the complete phasor diagram. Right now we are not introducing the winding resistance of the transformer or the drop which are occurring because of the winding resistance. So we are saying that V1 is still equal to minus of E1 towards the primary side. Okay. Now how much is the primary current taken at the instant of no load condition for a practical transformer? Is it going to be only Im now? No. Now this is a practical transformer, it will be having losses. That means now the current taken by the transformer has to perform two functions. What are the two functions? The very first function is to magnetize the core. So it will have Im, what is its function? Magnetize the core, it will be magnetizing the core. and one more component which I am calling it as IW, or the working component or the active component, which is also being called as core loss component. So this component will be making over with the losses which are occurring in the transformer at the time of no load. Now if at all I say what are the losses which are occurring at the time of no load condition. So if at all I say, once again, this no load current, which is the phasor addition of this Im and Iw, I call it as I naught. I naught is the phasor addition of Im and Iw, where Im is the magnetizing current responsible for the production of flux or for magnetizing the core. Iw is the component which is the working component which is responsible to make over with the losses. Okay, the addition, the phasor addition of these two will be giving me the no load current of the transformer, which is once again a very small current, right, nearly 2 to 5% of the full load current, right. This is once again a very small current. Again we will be plotting this. Once again, if at all I see this working component, we say that this will make over with the losses, but which losses? Is it going to make over with the copper loss and the core loss? Yeah, definitely. But at the no load condition, as we are saying that the no load current is very small, it is just 2 to 5% of the full load current, then obviously the copper losses which are occurring at the no load instant, how can we give the copper losses? PCU, it is given by I naught square into R equivalent, if at all I say, or in fact secondary side we don't have the current, so I must be saying R1, right. So I naught square R1, secondary side we don't have any current because it is at no load condition. So these are the total copper losses, but as the value of I naught is very small, these losses are not going to be very much significant, right. So this value is going to be very much small. So the majority of the losses which are occurring is only the iron loss or the core loss which are occurring because of the continuous magnetization and demagnetization as well as the eddy current. So the losses are only the iron losses or the core losses, right, and a very negligible amount of copper losses, right. That's why this IW is also being called as IC, core loss component, the active component, because this is making over with the majority of the core losses and a very negligible amount of copper losses. Okay, now continuing on with the phasor diagram. 5, we have plotted flux, even V1. Now where should be Im naught? For that, it is the phasor addition of the two currents Im and Iw. So where should be Im? Once again the magnetizing current, it should be in phase with the flux, right. Then Iw, the working component, that should be in phase with the voltage. It is looking over with the core losses, it should be in phase with the voltage. This is Iw. The phasor addition of these two will give us the I naught. The angle between V1 and I naught, this angle would be phi naught, working on lagging power factor load. Lagging power factor load means inductive load, right. So if the load is inductive and now the transformer is loaded, it is having winding resistance also, it is having leakage reactance also, it is, the permeability is higher, it is not that much, it is not infinite, but it is a larger value, the permeability is higher, the core is having a very high permeability, right. So all the properties of an ideal transformer are now not eligible over here, right. So it is a practical transformer, that too being loaded, fine. So once again starting with the very first phasor, the reference phasor, flux, we know this, then the induced EMF E1, then now can I say that V1 would be equal to E1 minus of E1. Now it is not an ideal transformer, neither the winding resistance is 0. Now the transformer is having the winding resistance as well and the transformer is having leakage reactance as well. So we will be having voltage drops. So what is the equation? What is the relationship between V1 and E1? Now V1 is equals to minus of E1 plus the drop occurring in the resistance and the reactance. So V1 must be equals to minus of E1 plus I1R1 plus I1X1. To have this V1, first I should have minus of E1. Let's plot this. Where is minus of E1? Opposite to this. Okay. Now next, I1 R1. I want to have the phasor I1 R1. This is a resistive voltage. If this is a resistive voltage, it has to be in the same phase as that of I1. Right? If it has to be in same phase of the I1, I first need to know the phase of I1. That means I first need to plot I1. Okay. And how much is I1? I1 is given by the phasor addition of I0 and I2 dash. Okay. I0 I know. I0 is the phasor addition of Im and Iw, that I know. Once again, I2 dash, what is this? This is minus the K times of I2. This is the loading component, right? Once you load the transformer, right, according to the load, the transformer draws an extra current, extra to the no load current, right? So that is I2 dash, and that is equals to minus of the K times of I2, that is in phasor, right? So I need to plot this, right? Then only I am going to get my I1. So for that, once again, I can plot I0. I0 is the phasor addition of Im and Iw. Okay. So this is I0. Fine. Now I2 dash. And for plotting I2 dash, I require I2, right? And for plotting I2, I require the loading details, because I2 is the load current, right? So the loading detail is, it should be having, it is a lagging power factor load. That means I2 will lag the secondary terminal voltage V2 by certain angle, phi 2, right? And to show this, we have to arbitrarily consider V2. So we'll be arbitrarily considering V2 somewhere in the third quadrant. Fine. Now, arbitrarily, if at all I consider that this is V2, then obviously I2, this is the lagging power factor load, so it will be having certain, the I2 will lag the V2 by certain angle phi 2, right? If I2 is here, where should be I2 dash? We have just learned that I2 dash is minus of K times of I2. Fine, K, say K is 1, or I may be assuming it K is greater. So if it is that, so it will be an antiphase to it. This will be I2 dash. Now once again, the phasor addition of I2 dash and I0 will result in I1. I1 is the phasor addition of I0 and I2 dash. Now we have got the phasor of I1. Okay, what is the phase of I1? Now for what I require this? We require it so that I can be plotting I1 R1, because to have V1, I know it is going to be minus of E1 plus I1 R1 plus I1 X1, right? So I want to have this voltage which is in phase with I1. Now I know that I1 is having this phase. Okay, if that is so, I1 R1 must be plotted in such a way that it should be in phase with I1, but should be added with minus of E1. Minus of E1 is here. So adding I1 R1 in such a way that it is in phase with I1. So I have drawn parallel to I1, right? Then the another phasor, that is I1 X1. This is what? This is an inductive voltage, right? If it is an inductive voltage, this voltage will lead the current I1 by 90 degree, because we know for a purely inductive circuit, the current will lag the voltage by 90 degree, or the voltage will lead by 90 degree. So this voltage will lead this corresponding current I1 by 90 degree, right? So the voltage has to lead the I1 by 90 degree, but I need not to add it to I1, right? I need to add it to I1 R1, right? So I'll be adding it to I1 R1 in such a way that it is leading by 90 degree, right? Now I may say, what is this phasor? What is this net phasor? This is V1. Now I may be saying that V1, this V1 is equals to minus of E1 plus I1 R1 plus I1 X1, right? Similarly, what is this phasor now? What is this phasor? Obviously, this is I1 Z1, right? The net drop occurring in the primary side. Fine. So, the primary circuit is completed. Now, coming to secondary circuit. In secondary, I am having V2, but I do not have E2, right? I need to plot the E2. What is the relationship between E2 and V2 in terms of transformer secondary? So, if at all once again I see E2 must be equals to V2 plus I2R2, the secondary resistance drop and the reactance drop. Once again, to have E2, V2 is already there, we have already plotted it, although arbitrarily. Then I2R2, once again, what is I2R2? This is a purely resistive voltage corresponding to the current I2. Both should be in same phase. I am already having the phase of I2. I2 is already plotted. This is its phase. So, I need to add I2R2 in such a way that it is in phase with I2. Fine. If that is so, add I2R2 in such a way that it is in parallel with I2, right? Then I2X2, that is once again an inductive voltage leading the current by 90 degree, right? Leading the current by 90 degree. So, it should be once again what this angle is supposed to be is 90 degree. And what is this net? This is E2, right? So, this is the complete phasor diagram of the transformer for a lagging load or inductive load, right? Similarly, moving on, if at all I say we want to have the phasor diagram of the transformer for a capacitive load. I want to have it for a capacitive load. It is once again the practical transformer having all these properties, but the only change is now if it is capacitive load. Quickly going on with the phasor diagram, once again it is flux, right? Then the induced EMF, primary induced EMF E1, then minus of V1. V1 is equals to, once again the equation is same. The relationship between V1 and E1 is V1 is equals to minus of E1 plus I1 R1 plus I1 X1, right? The phasor, obviously the phasor addition. So, I am having minus of E1 now, this is minus of E1. Once again I1 R1 I require, once again I1 R1, from where will be getting it? From I1, and for plotting I1 once again I require I0 and I2 dash. I0 is in same phase, it's the phasor addition of the two components IM and IW. Fine. Now I2 dash, just like the previous one, I2 dash is K times of I2 minus of K times of I2, and for this we need to now know the load, and this time the load is capacitive load. The load is capacitive means it has to be the leading power factor load, right? If that is so, once again quickly plotting V2, where should be V2? Once again V2 I am plotting it arbitrarily. Where should be I2? Now it is leading power factor, the current would be leading the voltage by certain angle phi 2. If I2 is here, where should be I2 dash? It should be minus of K times, say K, it is a step up transformer, step down transformer. The voltage would be stepped up, the current would be stepped down. So, I will be having I2 dash somewhere here. Now, I0, I2 dash, the phasor addition of these two will once again give me I1. Now, once I got the phase of I1, I can be plotting further, right? I1 is here, so I1 R1, it will be in the same phase as that of I1. I1 X1, it will be 90 degree. We have just discussed it in the earlier case. And now, what is this total? This is V1. So, V1 is equals to minus of E1 plus I1 R1 plus I1 X1. Similarly, secondary side, the relationship is E2 is equals to V2 plus I2R2 plus I2X2. V2 is already there. V2 is already there. Now what we want? I2R2 in same with phase with I2, but needs to be added with V2. So let's just extend it, but add it in parallel with it. So this is I2R2 and 90 degree to it, we are having I2X2 and this complete is our E2. So this is the complete phasor diagram of the transformer working for a capacitive load or leading power factor load, right? So what is the change what we just discovered between the earlier and this lagging and leading? The only change, if at all you say, the relationships for all is same. The relationship between E2, V2, E1, V1, it is going to remain same. The relationships for I1, I2 dash, I0, it is going to remain same. The only thing which is changing is the nature of the load, which is changing the relationship between V2 and I2. Earlier when it was lagging, the I2 was lagging the voltage V2. Now when it is capacitive load, the I2 is leading the voltage V2. Similarly, if at all I say, if it is for a resistive load, right? If it is for a resistive load, what is the change going to be? In this case, voltage and current is going to be in the same phase. No other difference. The same can be drawn somewhere here. If this is I2, in the same phase I may be showing V2. In the same phase I will be showing I2 R2 and now the I2 X2. So this is for the resistive load. This is for the resistive load. So now we have covered all the 5 phasor diagrams which are relevant with the topic in the third unit of the transformers which are mentioned in AKTU. Thank you so much.